Have you ever felt like you needed one single key to unlock 100 different doors? Well, in the super complex world of formal logic, that's a real challenge. Today, we're going to dive into a brilliantly simple solution to that problem, something called labeled tableaus.
Okay, so to really get why this one key idea is such a game changer, we first have to appreciate just how massive and complicated the universe of logic really is. I mean, think about it like this. Imagine you're a referee, but you're not just roughing one sport. You've got to officiate dozens, and every single one has its own completely different, super complex rulebook. It'd be total chaos, right? Well, that's pretty much the situation we're dealing with in logic. Yeah, a lot of people think logic is just one single thing, one set of rules. But that couldn't be further from the truth. It's really this huge, sprawling landscape of different systems, each built for its own unique purpose. And this is just a tiny taste. You've got modal logics, which help us reason about what's possible. You've got temporal logics for dealing with time, substructural logics for managing resources, and the list just goes on and on. And for the longest time, every single one of these needed its own custom-built proof system, its own rulebook. So staring down all this complexity, researchers came up with a really powerful idea. Instead of trying to build a new system from scratch for every logic, they figured out a way to adapt just one. And this is the light bulb moment. What if you could just take a standard method for proofs and just add one tiny extra piece of information to it, something that makes it flexible enough to handle all that crazy variety? Well, that one simple addition is the label. This really represents a fundamental shift in thinking. We go from asking a very simple black and white question, is this statement A true, to asking something much more interesting. Okay, but in what context is statement A true? And that little addition, that idea of context, changes everything. And the way this looks in practice is beautifully simple. You've got your statement, which we'll call A, and you just attach a label to it, in this case, the Greek letter sigma, using a double colon. That label, sigma, just tells you the specific context or world where A is actually true. That's it. So that's the big idea. But how does just sticking a label on something let us map out this entire universe of different logics? Let's take a look at how it actually works. A great way to think about these labels is as addresses. Seriously, they're like GPS coordinates. For logics that deal with possibilities or time, you can imagine all these different possible worlds. A label is what tells you exactly which of those worlds you're standing in at any given moment. So a proof ends up looking kind of like this. You start by saying, okay, statement A is true in world sigma. Then the rules of your specific logic might say that world sigma can see or connect to another world. Let's call it tau. The rules then let you travel over to world tau, and once you're there, you might discover that a whole new statement, B, is true. You're basically creating a map as you go. Now here's the really crucial part. By adding these labels, the unique properties of each logic, its fundamental meaning, get baked right into the rules for how you're allowed to use the labels. The logic's meaning becomes a part of the proof's grammar. It connects the abstract idea directly to the practical steps you take. And this isn't just some neat theoretical trick. This approach has massive practical benefits for both logicians and computer scientists. I mean, that tiny little addition of a label completely changes the game. By forcing us to be explicit about context, it lets people design proof systems that aren't just powerful, but also way more clean, more reliable, and just a lot easier to check. And the payoff here is huge. This method gives us some incredibly valuable properties. For instance, cut admissibility basically means your proofs are clean and direct, no weird, unnecessary detours. Completeness is a guarantee that if something is true, this system can actually prove it. Decidability means the system will always give you an answer. It won't just run forever. And the finite modal property is super important for computers because it helps them find errors and counterexamples automatically. And you don't have to take my word for it. The source material we're looking at today really nails it. The authors say that this method gives us a uniform treatment of various logics. That word, uniform, that's the whole point. It's about finding one single, powerful method to bring order to all that chaos. So let's zoom out for a second. This powerful technique isn't just a one-off trick. It's actually part of a much bigger, more unifying idea about how to structure logical proofs in general. What we've been talking about, labeled Tableau, they're part of a bigger family called labeled deductive systems, or LDS. This is a whole approach to logic that sees labels as this fundamental tool for managing information and keeping track of how all the pieces of a proof depend on each other.
And this is why it all matters outside of philosophy class. This core idea, using labels to track context, is incredibly useful in computer science for things like managing resources in a program, and it's essential in AI for building systems that can handle complex, real-world reasoning. So, we can end on this thought. Maybe the solution to a lot of our most complex problems isn't always about inventing something brand new from scratch. Maybe, just maybe, the most powerful innovation is finding a smarter way to organize and label the knowledge we already have.